Okay, so thanks for having me here. My name is Jiaxuan Li. I'm a grad student at Princeton University, graduating next year, so we'll be on job market this fall. So we've heard about like dwarfs in the cluster, more massive environments. So I'm going to shift gear and try to talk about satellites of the Milky Way or even lower mass groups. So dwarf galaxies are beautiful, as Aaron already showed. But they're also very important in terms of understanding dark matter and also our cosmological model. So one very simple exercise is that if you count their number, the sheer number could be compared with lambda CDM and try to see if our lambda CDM model is correct or not. So on the right-hand side, it shows the luminosity function of Milky Way satellites, which agrees currently with the model pretty well. So we no longer have a missing satellite problem. And it's not surprising at all that our best knowledge of dwarf galaxies come from the Milky Way satellites, just because they're pretty close by. And you can detect satellites down to a pretty low mass regime. So in order to put Milky Way into a broader context, in the past two decades, people have been trying really hard to survey other Milky Way analogs. And this beautiful figure made by Yao in the Saga team demonstrates the effort. Basically, we now have a very good understanding of satellites of Milky Way analogs from local group all the way to 200 megaparsec. And I'm going to claim that satellites of Milky Way analogs have been searched and studied very well. We need to move to the new regime. And what is that new regime? Let's look at some in-body simulations. So this is the simulation made by Ethan. It nicely shows one fact, that for a dark matter halo with different mass, they're all surrounded by subhalos. So subhalos, if you have a massive subhalo, it could host a galaxy. That means from cluster scale all the way to the LMC scale, they could all have satellites. So dwarf galaxies should also have their satellites. And the number of satellites around dwarf galaxy is relatively unknown so far. And we don't know whether they agree with the lambda CDM or not. And we don't know the properties of satellites of dwarf galaxies. And maybe we'll find something interesting there. So we started thinking about this, and we found, okay, people have been thinking about this for 10 years. And this is what's there in the literature. And this is a busy plot, but I'm going to guide you. So here I'm I'm plotting the dwarf galaxies as circles. The circle size is proportional to the virial radius, and each dot, tiny dot within the circle is a satellite. And okay, you might think, okay, we have a large sample, we can test the lambda CDM. But actually, no. So in this plot, the solid circles are isolated hosts, meaning that they're far away from any bigger groups. And you will notice that only a handful of such systems exists. And in literature, many systems are non-isolated, and that's a problem. So now let's imagine that we're sitting in another NGC, whatever galaxy, like 10 megaparsec away, and we're studying the Milky Way. The Milky Way will be like this. And we want to know whether the small Magellanic Cloud is a satellite of LMC or it's a satellite of Milky Way. And how do we know? We don't know, right? We don't know whether LMC brings SMC together or SMC is there with Milky Way at high redshift. So this highlights the importance of studying isolated systems, because in that case, we don't have this ambiguity of assigning satellites to the host. And this is the same for a simulation, because you still have to assign satellites to the host in simulation. So we need to study isolated systems. And in literature, there are only 6 such systems, which is not good enough to test the lambda CDM. And the crosses over there shows that these satellites are candidates, actually. Candidates means that we don't have distances to confirm those, and that's a big problem. So for example, you can have so many candidates, but only 30%, 20% of them are real satellites. So you need to measure their distance and see if the distance of the candidate agrees with the host distance. So as astronomers, we all know measuring distances are hard. And it's particularly hard for dwarf galaxies because they're faint and they're tiny and they're probably quenched. You don't have emission lines to measure spectroscopic redshift. Okay, so then to solve these problems, we started the ELVES-Dwarf survey. The goal of this survey is to search 30 to 40 isolated dwarf hosts at a distance range from 4 megaparsec to 12 megaparsec. I know this distance range is like very, very local for like many of you in the audience, but that's what we call local volume. So we select host galaxies to have a stellar mass from 10 to the 8 to 10 to the 10. This roughly covers from LMC to SMC and below, a little bit below SMC. And we want to see what's their satellite population. So what we do is we search for satellite candidates in existing ground-based imaging data like decals, and we're pretty complete to absolute magnitude of -9, which is about 10 to the 5.7 in stellar mass. And after having candidates, we need to measure their distances. And because these candidates are faint, measuring distances is not easy. So we use some technique called SBF, surface brightness fluctuation, and it's actually very interesting. So if for those of you who don't know what is SBF, this is a nice demonstration. So this figure shows the same galaxy population at 3 different distances. The leftmost panel shows the galaxy at 0.5 megaparsec, where you can see individual stars. As you move to the right, you move to 8 megaparsec, you see your image is like very smooth. So the smoothness or the pixel-to-pixel variation can actually quantify your distance. And for SBF, we don't need to take spectrum. It's image-based, which is relatively cheap. And using ground-based data, you can measure SBF distances for dwarfs out to 12 megaparsec, which is pretty nice. And compare with the spectroscopic surveys, which is actually biased towards star-forming dwarfs because for those dwarfs you have emission lines. SBF is now biased towards blue star-forming dwarfs. Actually, you can measure SBF pretty easily for red-quenched dwarf spheroids. Okay, so with SBF, we can measure distances and we can associate candidates with their hosts. And we published the first result of ELVES-Dwarf survey summarized here. The blue circles are the 8 new hosts that we surveyed, and we discovered 6 new satellites associated with these 8 hosts. And so for like six of the hosts, they're around SMC mass, 10 to the 8. So these are really low mass systems. And these are the new satellites confirmed. The bottom row shows the high resolution deep HSC data. They're like beautiful SBF-y looking dwarfs. So one simple statistics you can do is to count for the number of satellites per host. So here I'm plotting the results from this work in red, and I'm plotting the NSAT for more massive Milky Way-like hosts in green. So you can see a nice trend that more massive hosts have more satellites. But the question is, does this agree with simulation or any kind of lambda CDM prediction? To make the prediction, we use SetGen, written by Fangzhou Jiang. So SetGen is a semi-analytical model for satellites. What it does is that it initializes subhalos and evolves subhalos under the influence of a big halo. So after running SetGen, we populate the subhalos using 2 different stellar-to-halo mass relation. One is the Mann-Wattgard 2022, which has a relatively high amplitude and large scatter. The other extreme is from Danieli 2023, which has a lower amplitude and a tiny scatter. And we want to see which one is more realistic and which one agrees better with the observation. And this figure shows the prediction in the orange band. So overall, the data agrees with the prediction pretty well. So I don't think we have a missing satellite problem in this low mass regime. However, if you compare this stellar-halo mass relation with the Danieli et al., you will find that Danieli et al. Predicts a lower NSAT. So the number of satellites could give you some important information on the stellar-to-halo mass relation. But again, you know, the host-to-host scatter is huge, so it's really hard to say whether, you know, we disfavor Danieli et al. Or we disfavor the previous stellar-halo mass relation. And we need a big sample to really pin this down. Another angle to look at data versus model is to see the stellar mass function for individual hosts. So here I'm showing the 8 hosts. For the Mann-Waldkar relation, it agrees with the model very well. For the Danieli relation, we do find that 2 hosts, they don't agree with the model. So this probably means the Danieli model is not wrong, but maybe the scatter is just too small to encompass the diversity of the stellar mass function. Another interesting way to look at this is that you can plot the satellite over host mass ratio. And there's a very nice paper by Sadis et al. 2013 saying that if you plot the ratio function, this should be independent from your host mass. And I'm overplotting the Sadis et al. In purple and our data in blue, so it has a pretty good agreement with the Sadis model. Okay, so far so good. Another aspect of looking at the satellite is trying to see their quenched fraction. For Milky Way satellites, they're mostly quenched. The quenched fraction could be as high as 80% shown in the left. And we are wondering what's the quenched fraction for satellites in lower mass groups. The quenched fraction is really low, as shown in the right panel. So the y-axis shows the color. Redder color means quenched. Bluer color means not quenched. So as you can see, 5 out of 6 satellites are star forming. That means a pretty low quenched fraction, which is in sharp contrast with the Milky Way satellites. There are simulation papers claiming that the quenched fraction of LMC-like dwarfs, satellites of LMC-like dwarfs is high, but our results disfavor a high quenched fraction. Okay, because I don't have time, I'm going to move to a new topic. So there are 2 new surveys focusing on satellites of dwarfs. ELVES-Dwarf is one. There's also ID Mage by the Dartmouth group. So I think maybe by next year we'll have a pretty good understanding of satellites in lower mass groups. Okay, I'm going to move to the field because we heard about galaxies in the cluster, in the Milky Way groups, in lower mass groups. I'm going to move to a completely different environment. So hedgehog. Okay, so we discovered a new cute little galaxy in the field. It's very isolated, and we named it as hedgehog because you can see the emoji of hedgehog over there. Maybe the green star is the eye. It's spiky-ish. Looks like a hedgehog. And what's special about this? So there are only a handful of known field dwarfs that is quenched. Most of the dwarfs in the field is not quenched, it's star forming. But hedgehog is quenched, it's super isolated. So we measured its distance using SPF, putting it at 2.4 megaparsec, and the right panel shows the 3D environment of hedgehog. There's nothing within 1 megaparsec, so no neighbors within 1 megaparsec. So I'm calling it the loneliest hedgehog in the universe. And it has a stellar mass around 10 to the 6, making it really interesting why it's quenched. We all know that there are different quenching mechanisms for field dwarf. One really compelling mechanism is reionization quenching. But people have been talking about reionization quenching for lower mass dwarfs, like below 10 to the 5, they're probably reionization quenched. But the quenching efficiency depends on the halo mass. Maybe hedgehog has a low halo mass, making it easier to be quenched by reionization. So I'm trying to make the case that hedgehog is the most massive reionization puzzle we discovered so far. And we got 30 orbits, HST time, so we can construct a star formation history and really test out whether it's quenched by reionization or other mechanisms. So looking to the future, I'm really excited about LSST and Roman to do SPF for dwarfs to a larger volume. For LSST, you can find dwarfs and characterize all the dwarfs within 20 megaparsec using SPF. And this sample will be across all different environments, from satellites to field dwarfs. With Roman, because of its coverage in the near-infrared and high resolution in the space, you can actually push the local volume definition all the way to 100 megaparsec using SPF. And you gain a lot of volume in that way. So yeah, I'm really looking forward to working with Roman and LSST data in the future. Okay, I'll leave my summary slide here and take questions.
questions? James?
So I know this was not the main focus of your talk, but in the plot on the left, I was struck by the large scatter among the Milky Way size systems, and the models not having enough scatter there. So like, what's going on there? Like, is that a surprising amount of scatter for satellite counts among Milky Way hosts? I know that's not what you focused on, but I wonder what your thoughts are on that.
Yeah, so I think we have a pretty good agreement on the Milky Way side, but maybe the model shown here is not optimized for the Milky Way because when you run SetGen, you have to include the disk component for the Milky Way satellites. Here, the model is optimized for dwarf hosts. So I think it's not that big of a problem. People have been comparing the ELVES results with all kinds of simulations. It seems like fine in those comparisons.
Okay, more questions? Aaron?
Thanks. I'm confused about the plot you showed from the literature, predictions that might have been from Salas on the numbers of satellites versus mass ratio. The dark matter scale free, but in stars it shouldn't be. Like, for example, if you had a 10 to the 10 mass host halo, at some point you start running out of satellites because they don't form stars. I mean, so I don't understand this prediction here.
So this prediction depends on. So you have to assume that your stellar to halo mass relation is a power law. Then you have this prediction, and yeah, I think that's my understanding of this. But we can chat later.
Quick.
What causes the shape of the hedgehog? A slit, or what gives it a strange shape?
Yes, so the shape is not extremely elongated. It's kind of circular. But again, I would say, this bright star impacts your measurement of the shape. And with the HST data, we'll do a better job on characterizing the shape. But yeah.
There was no missing satellite problem, but around 10 to the 9, it looks like there might still be one. They're finding not enough satellites around there. I was curious to comment.
Yes, this is a very good point. We also noticed that there seems to be a dearth of satellites around this mass regime. So in our upcoming paper, we'll have we'll have a larger sample, especially sampling this mass range. And just looking forward to that paper. Yeah, we'll discuss it.